Alright, so I don't know if that first video is saved or not, but who cares? I have to do this anyhow, right? Oops, I should stop talking because now I'm being recorded. Anyhow, we found four. Where the heck did we get to? Here we go. We needed four boundary conditions, and we found four suitable boundary conditions. So we have the concentration of helium at y equals 0. We'll use I for the interface and h for the top height. So at y equals 0, Ca, that was our initial concentration, right? That was Ca naught. Ca, say S, at y equals yi, the interface, equals Ca P at y equals yi. Okay? And also at the interface, we have the slope, so negative d, well, let's say AS, so the diffusion through the silicon dioxide times the slope is equal to, so we're setting flux is equal, the diffusion through the Pyrex, and this is the slope on that respective side. And finally, as we march through the system and get to the top, we have the concentration of A at y equals h equals 0. Let me tell you guys, this is a system of equations that can take you a little bit of time and a few pages to solve. I've done it. I've asked people to do it on exams, plenty. If you have a take-home exam, I would absolutely ask you to do this. But this is just a system of equations. I essentially start plugging in and solving. I would probably start with Ca of y equals h, Ca of y equals 0. I'll apply my two Dirichlet boundary conditions first. After I apply those, it's kind of a crapshoot as to what I start solving for and what I start replacing. I would say we'll go over some general rules of how to start solving these, but I'm not going to go through the full derivation. I already have this solved, this exact problem. I solved it over spring break. It's all typed up nicely, so we'll look at it. But let's say to start applying these, I recommended that we started with the Dirichlet boundary conditions first. So Ca of y equals h. Well, that applies to the silicon dioxide. So this is C3H plus C4. And that was equal to 0. All right, I'm going to try this one too. Ca of y equals 0 equals, so at y equals 0, I'm in the Pyrex. C1 times 0, so 0 plus C2. C1 times 0 plus C2. This equals to Ca naught. So actually, there we go. We have one boundary condition already, or one of our integration constants. I'm sorry, not, well, we have all four boundary conditions, but we've solved for one integration constant already is C2. We found that that's Ca naught. So we got 1 out of 4. All right, and so I can also evaluate this boundary condition, the one that has to do with the concentration, by just plugging in y sub I for each of these. So my next boundary condition that I want to look at is going to be this one. So CAS evaluated at y equals y sub I is C3 y sub I plus C4. That's equal to the concentration in the Pyrex at y equals y sub I. So it's just C1 y sub I plus CA naught. All right, so that's our third equation. And our fourth equation is going to be, we can write this as a ratio. In fact, let's evaluate this. dCA dy in the silicon dioxide, the differential change with respect to y here is just C3. The differential change in A, the concentration of A with respect to y on the Pyrex side is just C1. So, excuse me. Diffusion of A through the silicon dioxide times C3 equals the diffusion of A through Pyrex times the differential change in the Pyrex with respect to y is C1. And there's the system of equations to solve.